A lot of work that the department does goes beyond just fundamental research and is also towards direct industrial application. And while most Department of Physics across the country only offer science degrees, here at IIT Madras, BTech in Engineering Physics and MTech in Functional Materials and Nanotechnology are offered.
In every convocation since 1964, everyone has looked forward eagerly to the award of the President of India Gold Medal. It would indeed be very disappointing if the awardee is not present here with us for the first time. Rajat informed me that he would try to be here in person.
IIT Madras has a large number of students and faculty, and a lot of projects are going on. In any big university or institution, the computing center is usually the heart of the system. PG Senapati Center houses all of these things. Many different points need to be networked together to use all our services.
IIT Madras network has 3 zones, namely Academic Zone, Hostel Zone and Residential Zone. Our academic zone is completely Wi-Fi enabled. We have powerful network firewall which is protecting our campus network from outside world.
ERP solution that is implemented in IIT Madras. This application is called Workflow. This is being used by IITM faculty, staff and their students. High-performance computing environment is set up to cater the increasing demand in computing facilities of the researchers of IIT Madras.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become
Muted.
Yeah. Hello and good evening to everyone. Thank you for joining with us today. This is Lisa from the Office of Global Engagement at IIT Madras. It's my pleasure to welcome you to the 56th webinar from the IRIS webinar series. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them to become world-class teaching and research institutes. IIT Madras is proud to have been selected as one of the such Institute of Eminence. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. As part of this initiative, the IRIS webinar series aims to showcase the innovative resources that are being generated to various stakeholders like students, researchers, industrialists, and policymakers. From the microelectronics and integrated circuits technology cluster, the research initiative being presented today is titled Advanced Memory and Computing, which is led by Professor Anbarasu Manivannan. Professor Anbarasu Manivannan is a professor in the Department of Electrical Engineering and jointly with the Department of Physics as an interdisciplinary faculty member in the area of phase change memory technology at IIT Madras. His research group focuses on the development of phase change memory, 3D X-point memory, multi-bit data storage technology for high-speed non-volatile memory applications, and also phase change synaptic devices for neuromorphic computing through interdisciplinary research, including design of novel material, structure property correlations, device and technology for high-speed computing. Professor Anbarasu's research group contributed more than 60 international journals and conference proceedings, and they have 3 Indian patents. Professor Anbarasu currently serves as a member of European Phase Change and Ovonics Symposium. Today we have Dr. Bhashwar Chakrabarti as another speaker today, and he is one of the co-PA in the project initiative. He is the assistant professor in the Department of Electrical Engineering at IIT Madras. Dr. Bhashwar manages the emerging nano devices for information processing laboratory. His research group investigate emerging electronic, optoelectronic device and beyond CMOS computational frameworks. Dr. Chakravarti has made several key contributions to the area of memoristic neural network, including first demonstration of monolithically integrated 3D CMOS, memoristic dot product engine, and a memoristic multilayer perceptron network. He has published about 30 papers in international journals and conferences. He has 1 US patent and a book chapter. Professor Supratik Guha has joined as a moderator today, and he is a professor at Pritzker Molecular Engineering and senior advisor to Argonne National Laboratories, Physical Sciences and Engineering Directorate, leading the lab's microelectronics and quantum information science strategic efforts. Before joining Argonne and the University of Chicago in 2015, he spent 20 years at IBM Research, where he last served as the Director of Physical Sciences. At IBM, he pioneered the materials research that led to IBM's high dielectric constant metal gate transistor, one of the most significant developments in silicon microelectronic technologies. Dr. Guga is a member of the National Academy of Engineering and fellow of the Materials Research Society, American Physical Society, and the recipient of the 2015 Prize for Industrial Application Physics. It's really our pleasure to have you all up today. Before we start, a note to the participants, kindly use the Q&A box to enter your question and also upload the question that interests to you so that the moderator can prioritize later. Over to you, Professor Anbarasu. Thank you.
My slides are visible?
Yes.
A very good morning, Professor Supratik Guha. Thank you very much for accepting our invitation. The entire team of Advanced Memory and Computing is extremely happy and honored to have you as the moderator today. A very good evening, one and all. Welcome to IIT Madras Research Initiative Spotlight Irish webinar on Advanced Memory and Computing. My name is Anbarasu Manivannan. Today, I would like to present to you an overview of the center and highlights of ongoing research activities as well as future plans. Outline of my presentation as follows. At first, I would like to briefly mention about the necessity for high-speed computing devices that sets the genesis of our center. Then I will give you an overview of our center with the team members involved, collaborators, and also research facilities. Subsequent to this, I will briefly mention about some of the thrust areas as well as the technology development at the center. Finally, I will discuss about some of the key results on phase change memory technology and some of the milestones which has been achieved until now. And towards at the end, Professor Bhashwar Chakrabarti will speak on resistive random access memories and its milestones. Memory is an essential component of modern electronics that shapes today's knowledge and information-based society. In the year of 2016, International Data Corporation predicted that the global digital information by 2025 as 44 zettabytes, which is nothing but 44 billions of terabytes of information. However, very interestingly, the actual data produced until 2020 is about 64 zettabytes. This is about 50% increase than the predicted value. This is primarily owing to a pandemic situation. With this increasing rate, we may expect by end of 2025, the digital information available on Earth is going to be 175 zettabytes of information. So I would like to bring your attention here. In the year of 2010, the total digital information available on Earth was only 2.6 zettabytes. In the subsequent years, the digital information have been enormously increasing in the exponential order This is primarily owing to advancements in various key areas, including advancements in Internet of Things, development of smart city, advancements in healthcare, science and technology, security, government, and so on. So altogether, about 49% of the actual data that remains in the public cloud and 30% of the data in the worldwide that requires real-time processing. This clearly indicates the fact that the computational demands that exceeds the existing processing capability, for which let us try to understand the computing architecture in the present times. We know that memory devices are broadly classified into two categories, namely non-volatile and volatile memories. Flash memory known to be non-volatile in nature, but it suffers because of the slower programming speed in the range of microseconds. On the other hand, random access memories are very fast in programming in the range of nanoseconds, but it suffers because of the volatility in nature. Now, the obvious question is, when we have such matured semiconductor memories, such as flash and random access memories that can satisfy the current demand, then why do we need to go for new memory technologies? So achieving high-speed computing, there are two major obstacles which we will see one by one. The first one is scaling of conventional memory devices. Basically, flash and random access memories mainly relying on storing electrons or charges as their memory mechanism. Upon scaling, the number of electrons that are getting diminished, thereby continued scaling becomes very difficult. The second most crucial problem is the data transportation between the processor and the memory. If the processor wants to retry information from any of the volatile class memories such as DRAM or SRAM, then it requires only few tens of clock pulses. On the other hand, if the processor wants to retry information from its storage class memories such as flash or hard disk drive, then it requires few tens of millions of clock pulses, which means until then the processor is idle. Therefore, the overall computing speed is heavily compromised. This situation necessitates for the development of high-speed non-volatile memory. Among various emerging memory technologies, phase change memory as well as resistive random access memories are considered to be the leading contenders to satisfy next generation high-speed non-volatile memory technologies. The fundamental principle primarily based on rapid and reversible switching between high resistance and low resistance states by means of nanosecond electrical pulses. The stability of these low and high resistance states are establishing higher data retention, and the rapid and reversible switching between these two states enable extremely faster programming. So by knowing these superior characteristics, it is possible to envision the high-speed non-volatile memories based on PCM as well as RAM technologies. Now, it is important to look at three broader avenues wherein the high-speed non-volatile memories can be achieved. The first one is 3D explained memory, which is jointly developed by Intel and Micron. This offers extraordinarily better scaling capability because of its new selector device that is primarily a chalcogenide-based OTS selector that offers better scaling compatibility with the PCM layer, and therefore one can envision three-dimensional memory devices to enable high-density data storage solutions. The second most possible avenue is multi-bit data storage. Within the same footprint, we will be able to enable high-density data storage if one can enable multi-bit data storage technologies. So PCM as well as RAM enables these two lines as 3D explained memory as well as multi-bit data storage to have high-density non-volatile memory solutions, particularly in the von-Neumann architecture. Now, the third avenue is nothing but neuromorphic computation, and phase change memory as well as resistive random access memory provides an unique platform to enable computing architecture beyond von Neumann situation. So all three possible avenues essentially provides solution for high-speed computing. This sets the major theme of this center to enable high-performance non-volatile memory devices as well as brain-inspired computing technology as solutions. And this can be achieved through two different technology nodes, namely phase change memory as well as resistive random access memories. We would like to systematically investigate and develop various technologies as listed here. Next generation non-volatile memories, 3D explained memory, multi-bit data storage solutions, as well as universal memory, and finally neuromorphic computation. As you can see on the right, 3D explained memory as well as multi-bit data storage solutions provide platform in the von Neumann architecture, whereas neuromorphic computation provides computing solution in the non-von Neumann architecture. Having these new technologies, it is important to set a common agenda to address or develop advanced memory technologies based on this, and that essentially requisites multidisciplinary research activities. Therefore, the team members having various expertise to design novel materials, understand their local structure and physical property, as well as explore the transport properties, device modeling and simulation, fabrication of nanoscale devices, and testing with ultra-fast timescales, as well as exploring their system integration as well as reliability that requires various expertise to address the common goal. And therefore, our team members necessarily having various expertise to address this common goal. In addition to this, we have international collaborators who have been contributed excellent way in two broader areas, namely phase change memory as well as resistive random access memory. In the domain of phase change memory, Professor Matthias Wuttisch from Aachen University, who has expertise on design of phase change materials as well as metavalent bonding. Professor Harish Bhaskaran from University of Oxford, who has expertise on phase change photonics as well as optoelectronic frameworks. Professor Ritesh Agarwal from University of Pennsylvania, who has expertise on phase change nanowire devices. Professor Riccardo Mazzarello from University of Rome, who has expertise on ab initio MD simulations of phase change materials. And in the domain of resistive random access memories, our moderator today, Professor Supratik Guha, has expertise on development of high quality resistive materials as well as MBE systems and oxide-based thin film materials as well as quantum computing. And Professor Sankara Narayanan from University of Illinois has expertise on MD simulations, machine learning, and Professor Anand Raghunathan from Purdue University has the expertise on neuromorphic computing. Altogether, contribute towards development of advanced memory and computing. In addition to that, we have industry partners, namely Micron Technologies as well as Western Digital. They have been consented to be part of this center. So having this common agenda, we have been fortunate to have the clean room facilities at IIT Madras, namely in CNNP. We have clean room as class 100 as well as class 1000 to fabricate the devices using E-beam lithography as well as photolithographic tools. And subsequently, we have been able to characterize these devices using the facilities that are available with CNNP. And as part of the COE grant, we have been able to capitalize some of the major research facilities that are required for memory research, mainly memory array tester, advanced programmable electrical tester setup, as well as current controlled multi-level switching setup and temperature dependent resistivity measurement. All these supports for the development of for the research aspects of development of advanced memory and technology. And we have been able to concentrate or focus on some of the major thrust areas as listed here. Development of new materials to enable superior characteristics of the devices, and that certainly requires strong understanding on the materials and ultra-fast dynamics that comes with the capability of rapid and reversible switching between two resistant states, namely amorphous and crystalline states, and understanding the mechanism of threshold switching or electrical switching that defines the speed of memory devices. And the fourth one as development of PCM as well as RRAM devices and enabling ultra-fast testing capabilities. And the fifth one as brain-inspired computing by means of PCM as well as RRAM devices to enable neuromorphic hardwares. And the potential engagement and the aspirants who could have different backgrounds possibly can contribute to the center. For example, students, researchers, or scientists from the background of chemistry, material science, physics, computer science, and nanoelectronics can also become part of the center. And for example, to explain this, the important role of the chemistry here is chalcogenide materials do have a new bonding mechanism known as metavalent bonding. This satisfies some of the unique fingerprints to identify new materials. Hence, this also satisfies the research thrust for the chemist as part of this center. So those who are interested to become part of the center may wish to write email at kamak.iitm@gmail.com. This concludes the first part of my talk. And now I would like to briefly mention about some of the milestones achieved in the domain of phase change memory technology. Reversible switching in chalcogenide materials discovered by S.R. Wojcinski in the year of 1968 is one of the most fascinating property that led to develop phase change memory technology. Around at the same time, the co-founder of Intel, Gordon Moore, who developed the first amorphous semiconductor memory based on the concept proposed by S.R. Wojcinski, and he claimed that such amorphous memory can surpass the existing conventional memory technologies at some point in time. So his words became true after 5 decades, and we could see that Intel and Micron jointly launched a new product line called 3D expand memory that offers 1,000 times faster than the existing NAND flash and 1,000 times higher endurance as well as higher density. So having this scenario, the fundamental origin of electrical switching in chalcogen materials is very fascinating property. And in his seminal paper, S.R. Wojcinski described as follows. Initially, the material is in the high resistance amorphous state. When an appropriate voltage pulse is given to the device, as soon as the device realizes the critical voltage known as threshold voltage, the device switches to the conducting state. If the on-state current is sufficient to crystallize the conducting channel, then for the removal of the applied voltage pulse, the low resistance state is permanently removed, meaning one can achieve a memory switch by means of applying a suitable voltage pulse that can switch a material from amorphous state to a low resistance crystalline state. On the other hand, if the on-state current is not sufficient enough to crystallize the conducting channel, then for the removal of the applied voltage pulse, the device retraces back to the initial high resistance, which mimics a perfect on-off threshold switch, which can enable two-terminal transistor device. That's how these two configurations of a memory as well as harmonic threshold switching behavior enables a vertically stackable array configuration in the 3D expand memory. So it is important to see that the common property between memory switch as well as threshold switch is nothing but a threshold switching behavior. So it is the factor that the threshold switching essentially decides the programming speed of a phase change memory. So let us look at one of the switching characteristics of OTS device. The right side view graph, which depicts the threshold switching characteristics of GET6 based OTS device, wherein we could see that the device switches to the conducting state after certain delay time of TD, and the on state is retained until a minimum voltage known as holding voltage, below which the device switches back to the initial high resistance. So this clearly tells us that by means of understanding the threshold voltage as well as holding voltage, one can rapidly and reversibly switch back and forth between on and off states in faster time scale. Now the obvious question is how fast these devices can switch. It is nothing but 2 nanosecond time scale. So this 2 nanosecond is a magic number. It is not the inherent property of the material. However, it is the measurement limitation. So in order to overcome this measurement limitation, as well as to understand the inherent property of the device, we have developed an advanced programmable electrical tester setup at IIT Madras. So this setup can enable time-resolved measurements starting from 100 picoseconds. This is possible because of the custom-built high-frequency contact boards, which can capture the current voltage characteristics in faster time scale. So by utilizing these advanced programmable electrical tester setup, we have been able to explore numerous memory devices, and I would like to highlight 2 different types of PCM devices here. On your right, indium antimatter tellurium based PCM device, which shows the peculiar characteristics wherein the device can switch with longer delay time for the lower applied voltage pulse. And if the applied voltage pulse amplitude is increased in the higher range, then the delay time decreases into much smaller value, as small as ideally 0 or within the measurable limit of 50 picoseconds. This situation gives us a clear understanding that one can achieve extraordinarily faster switching when the applied voltage is almost twice that of the threshold voltage. So most of the phase change memory devices having variety of active materials follows this voltage dependent characteristics, and because of the greatness of the setup, we were able to enable sub-nanosecond threshold switching characteristics of a variety of devices. And on the right hand side, we can see that the second family of the phase change material, which is known as silver indium doped antimatter tellurium device, wherein we can see that the threshold switching takes place at the critical voltage of threshold voltage itself without any measurable delay. This is an extraordinarily faster threshold switching without any measurable delay, which means the speed of the threshold switching is essentially dictated by the rate at which one can reach to the threshold voltage. So materials of this category can enable PCM device with even SRAM-like speed. So now by having these 2 different types of voltage dependent characteristics, it is important to look at the analogy to enable high-speed computing. So let us assume that this is the energy barrier to overcome the conducting state or to reach the on state. Now, when we provide a lower energy, which is reasonably smaller, that may not be sufficient enough to overcome the barrier. And if sufficient energy is provided, at some point in time, it is possible to overcome this barrier. And thirdly, if the applied energy is significantly higher, then it is possible to overcome the barrier in the faster time scale. When the applied energy is significantly higher, then the speed at which one can reach to the conducting state is extremely faster. So having this analogy, we could look at the experimental data. If one wants to switch the device in faster time scale, even up to 10 nanoseconds, then the applied voltage pulse is merely equivalent to the threshold voltage. If one wants to switch the device below 10 nanosecond, even up to 500 picosecond, then the applied voltage must be 1.5 times of the threshold voltage. Now, the third condition, when the device needs to be switched at extremely faster time scale in few nanoseconds, then the applied voltage must be twice that of the threshold voltage. So most of the materials follow this strategy, and wherein we could enable high-speed switching of these phase change memory devices. The second family of phase change material does not follow this strategy, whereas it offers extraordinarily faster threshold switching with low electric field itself. So by having these different strategies of switching effects in picosecond time scale, it is possible to visualize PCM device even with SRAM-like speed in the future. The second most critical milestone which we have reached is the multi-bit capability of the phase change memory device. We have been able to explore a variety of materials-based PCM device to identify multiple level switching in various phase change memory devices. We have been able to explore at least 8 stable levels in indium antimony tellurium-based materials, as well as silver indium doped antimony tellurium-based materials offers more than 16 levels in a stable fashion to enable 4-bit memory process. So altogether constitutes high-speed, high-density memory device configuration. So with this, we would like to explore, as mentioned here, with respect to the PCM technology roadmap in the coming years, we would like to explore on development of high-speed non-volatile memory devices, as well as we would like to work on 3D expand memory by combining the architecture of harmonic threshold switch along with the PCM line to have high-density, high-speed non-volatile memory solutions. The third one as multi-bit data storage, where we were able to enable even until now up to 4-bit technology, and we would like to explore on 5-bit technology to achieve high-density data storage solutions. Finally, we would like to unify all the features into a single candidate which can surpass the existing memory technologies. So such situation can arise in the future, namely universal memory. The fifth one is phase change synaptic devices. This is mainly important for exploring the computing speeds beyond von-Neumann architecture to enable neuromorphic computing. With this, I would like to hand over to Professor Bhashwar Chakravarti to discuss on resistive random access memories and its milestones.
Okay. So am I clearly audible?
Yes.
Okay. Excellent. So a very good evening to all of you who are joining from India, and thanks for your attendance. Special thanks to Professor Guha for joining our session today, and good morning to you. So Professor Anbarasu has already spent some time discussing about the mission and vision of the center. I will, over the next few minutes, talk about the focus area 2 of our center, which is the resistive random access memory technology. So before I do that, let me just spend a couple of minutes to talk about the sort of the evolutionary history of RRAMs, just to give you a perspective of the technology, where it started and where we are right now. So the phenomenon of resistance switching was observed very early on in the 1960s. So T.W. Hickmott first observed the resistance switching phenomenon in anodic oxide films, and he called it negative resistance effect. So that was way back in 1962. So after that, in the late 60s, in the in the 1970s, there were several groups that started investigating resistance switching effect in different materials, mostly oxides, nickel oxide, TiO2, etc. But resistance switching, application of resistance switching as a viable technology did not occur until the early 2000s. So Samsung, for example, studied, they showcased a non-volatile memory technology with transition metal oxides back in 2005 and 2006. ITRI were instrumental in some of the key demonstrations in those years on hafnium oxide-based RRAMs. So their demonstration in 2008 in IDM was one of the highest performance hafnium oxide-based RRAMs during that time. Almost about the same time, Dmitry Strukov, who was working with HP Labs at that time, came up with this paper that is known as missing memory stuff found. So in that paper, he linked the resistance switching effect with the so-called memory strip effect that was proposed by Professor Leon Chua from Berkeley. So that paper caused a spark of interest, if I may, in this area of research, and many works followed. The industry started to, of course, invest in RRAM technology at the same time. So, for example, SanDisk developed a 32 gigabit array. Samsung, TSMC, they were all investigating RRAMs. So back in 2017, this startup company in Silicon Valley named Crossbar, so they first demonstrated this 3D crossbar memory integrated with CMOS technology. So right now we are here. So now the semiconductor manufacturing giants like TSMC, they are investigating RRAMs, mostly for embedded applications right now. So TSMC first showed RRAM technology first in 65 nanometer, then in 22 nanometer recently. And in 2021, this joint paper by TSMC and Stanford was published, but they have reported the world's first non-volatile deep neural network, which they have named it Chimera. So it has, of course, resistive random access memories have come a long way from these early studies to more of a system level application. There are, however, still challenges in terms of high power, in terms of variability, and those challenges, of course, limit. So far, they have been limiting the application of RRAMs in embedded, mostly for embedded scenario. So here at IIT Madras, we are studying some of these issues, some of these challenges, and we are trying to develop strategies of how to address them. So I will now focus on some of those strategies. So we are studying materials, we are trying to develop devices, and our final goal is to, of course, develop systems. So when it comes to materials design and device development, I'll just name a few strategies. The first strategy is to use doping or to use stoichiometric control. So here is one of our previous works where we can see that a substoichiometric titanium oxide film was used to develop this type of resistive memory crossbar array. It's a 2D crossbar array, 20 by 20. So the substoichiometric film is used to reduce operating voltages, which in turn reduces operating power, which is of course important. And that helped us to build this relatively large area in this specific example. So that is one of the ways we can reduce operating power. And then if we go to the next slide, the next strategy that we are looking into is the so-called electrode oxide or electrodielectric interfacial engineering. So the top two figures show an example of an oxygen and a metal oxide based resistive memory technology with graphene electrodes. So when we use graphene instead of conventional metals, we have shown that we could reduce the switching power by reducing the operating current below submicron ferrocene. At IIT Madras, we are also investigating the so-called interfacial resistance switching effect in OXRAM type devices or metal oxide type memories. So the bottom two graphs show that. So the interfacial switching effect has some advantages compared to the so-called filamentary devices. So interfacial switching reduces the cycle-to-cycle variability, which remains as one of the main issues in metal oxide-based RRAMs. So this interfacial switching effect was nicely utilized in our devices fabricated at IIT Madras. We can see that the switching voltages are low, approximately 1 volt, slightly lower. And what we can see, the interesting part is that the switching is unlike filamentary switching, the switching is not abrupt. It's more of a continuous switching, which is useful for neuromorphic applications, first of all. It is also useful to reduce variability. And on the bottom right figure, we show that multi-level programming is possible by using this memory device. So that is the materials and device design strategies that we are looking at. I'll talk about the system level applications in the next 2 slides. So this is a demonstration of a 3D crossbar memory array that is integrated on a CMOS based substrate. So the top right figure shows a CMOS chip. And on top of that, the memristive or the resistive memory crossbar array was integrated. The architecture of the RAM crossbar array is shown in the middle. And the top right figure shows the stack, the material stack for the device stack. You can see that the same titanium oxide, aluminum oxide stack was used, as I mentioned in one of the earlier slides. So when we integrated this crossbar array with the CMOS chip, we achieved multi-level programming in both the layers, in layer 1 and layer 2. And we were able to show the so-called vector matrix multiplication or multiply add operation, which is very frequently used in deep neural networks. It is one of the most frequently used operation in any deep neural network. So we were able to show that if we use this type of a hybrid CMOS RAM crossbar network, we can perform high density, high bandwidth vector matrix multiplication operation. So the next example is again a system level implementation, demonstration of a multi-layer perceptron using memristive crossbars. So these are oxide RAM crossbars. 2 such crossbars were used to make a feed-forward neural network, also known as multi-layer perceptron. So these demonstrations show our capability to fabricate and implement system level to implement systems in a sense. And with that, I would like to go to the next slide where this is essentially the RAM technology roadmap for us. Of course, we are investigating individual RAM cells. We are trying to design and develop RAM devices that have high switching speed, that are non-volatile, and show switching at low energy, and also have high endurance and data retention capability. So in addition to that, we are also looking at 2D memory arrays right now. We are, in addition, looking at threshold switching selectors that are used to reduce leakage in large crossbar arrays. The next goal is to fabricate 3D cross-point memory arrays and multi-bit RRAMs, of course. And the final goal, of course, is to develop neuromorphic hardware with these 3D cross-point memory arrays. So there are 2 potential applications we see. One, of course, is the already mentioned high density, high bandwidth vector matrix multiplication using 3D cross-point technology. That can go for cloud or server level applications for hardware accelerators. We are also investigating spiking neural networks. So that work is ongoing. We are already studying spiking neural networks using RRAM technology for different applications such as voice recognition and motion detection. So these two are the targets in terms of system level applications. So with that, I'd like to conclude. Thank you again for your attention. Now I'd like to leave the floor to Professor Guha, and we are all eager to know about his suggestions, his comments. So thank you all.
Okay, thank you, Professor Chakraborty and Professor Anbarasu. Can you all hear me?
Yes, we can.
Yeah, I enjoyed the presentation. Learned some things as well, particularly for phase change memories, which I was not that familiar with. So a couple of questions, right? So this has been, these technologies have been around for quite some time, but they have not made it yet in large scale applications, right? Because, you know, flash technology keeps improving, 3D flash keeps improving, but, you know, Professor Anbarasu, you noted that, you know, access times can be slow, etc. So what is holding these technologies back, PCM and these sort of filamentary memories that Bhashwar talked about?
Okay, so if you look at the history, the way how they have been able to commercialize, starting from the first demonstration was done by Samsung in the year of 2007, around at that time. And those chips were essentially employed in some of their mobile phones around in 2010. And they were able to clearly claim that significant power reduction as well as better speed in terms of the operations, the programming or the operating speed. And that is one of the interesting aspects which had happened in the year of 2010. And subsequent to that, Micron launched a variety of series and parallel products, mainly for embedded applications, that was withdrawn later in 2012 or so. With respect to the technology development, it appears to be the candidate, particularly PCM as well as RRAM, can enable a potential solution in terms of high-speed computing devices. With respect to the cost optimization is one of the bottlenecks which has to be overcome in the coming years. So in recent this year EPCOS meeting, European Patient Memory meeting, where we could learn from ST Microelectronics as well as IBM groups, clearly mentioning that PCM can find a market immediately in the area of particularly in embedded applications, whereas IBM Zurich group clearly claims that with respect to neuromorphic hardware, it is possible and they have been way ahead to move forward. And the overall perception is the cost optimization, which may take some more time to look at these products in the marketplace.
Okay. Bhashwar, before I ask you to comment, I will ask the audience if they have any questions to put it in the Q&A, and then I will try to summarize and place it to our speakers. Bhashwar, do you also want to add something to what Professor Anbarasu said?
Yeah, just one quick comment. So for RRAMs also, there are, of course, challenges. So I think one of the main challenges is the variability in filamentary RRAMs. That is one of the major issues. So that is why right now we are also investigating this type of bulk or interfacial type of systems. But I think in terms of technology, the maturity of technologies, RRAMs are for embedded applications, they're already there, as TSMC is showing us also. They are now doing that. For RRAM to replace flash, I think it's also, as Professor Anbarasu said, it's also a matter of the cost to do so. So RRAM, if we can address the issue of variability, I think it will be possible in the near future.
Okay. There is a lot of interest in what are called vector matrix multipliers, right? In computing, because of data intensive workloads, one has to do dot products of big vectors, right? And that takes a lot of energy because today you have to keep shuttling between, getting your information from SRAM or DRAM. So there's a lot of interest in dot product engines. And Bhashwar, for instance, I know that you worked on that, right? Where you have crossbar memories. If I really believe that if a crossbar memory could be built that is reliable, that has all the issues sorted out, it could be a hardware accelerator product that could be one of the most important circuit elements in computing today. What is your feeling about crossbar memory? So what I want you to focus on is not the good news, because I want you to tell me the bad news. What is the problem? What is stopping all this?
So Professor Anbarasu, would you like to answer first about phase change? Then I can.
Okay. So there are a few bottlenecks which has to be worked on, particularly the challenges in terms of the technology development. Number one is resistance drift in the amorphous space. If we talk about multi-bit data storage, then certainly at higher resistance levels, there is a significant drift that might be an issue in terms of reliability. As far as 2 bits concerned, the stability is significantly larger. But if one wants to go for high density, then of course, there are only 2 possibilities. One is 3dx point or otherwise multi-level switching. So these are some of the potential issues. As well as the mechanism of switching itself is not fully understood so far, the origin of the switching itself. So this could be one of the potential avenues where such understanding can throw light on the selector device itself. So this is one of the other bigger problems to look at.
Okay. Okay, I will ask you a question from the audience. It's a sort of, well, 2 questions, let me say, both together, and maybe give us short answers on these. What is your view on using organic material-based, memory, non-volatile elements for neuromorphic computing or other computing? And the second question is, do you feel someday they can embed RAM and storage class memory in one drive or in one package? So, Professor Anbarasu, why don't you take?
Yeah, so I'll take this. Maybe the last question first. Probably that's the overall expectation, to have a kind of universal memory that can encompass all the features into a single candidate. So if we look at the possible ways how they can move ahead, considering the present times as flash memory. So flash memory certainly provides enormous capabilities to store the data as well as better processing. But as far as the speed concerned, or the programming speed concerned, still it is not sufficient for us. And we cannot go beyond a certain time scale. This is primarily because of the fundamental limit of the programming aspect itself, because the nature of changing the threshold voltage itself is gradual. So it's obvious that tuning the threshold voltage from VT to VT prime, it takes some time, and one cannot surpass certain time scale in the microseconds. Now, what is possible if the candidates among emerging memories, if anyone can sit closer to the flash memory to have a hybrid solution, wherein we can use the emerging memory as an accelerator, as you rightly pointed out, and then storage can become the candidate as a flash. So in such situations, we will be able to visualize the capability of this emerging memory, as well as we can also see the potential of taking over the entire space in terms of better memory in the computing architecture. This is one of the ways where I think even the Intel Micron, they were trying to look at having the hybrid configurations to move forward. It's one of the ways to move forward. I'm not aware of the organic materials, particularly. I think Bhashwar can take up this question with respect to using the organic materials. in terms of high-speed non-volatile?
So certainly that's actually a very interesting question. Organic memories are certainly possible. I mean, different groups across the world, they are developing organic memories. But I would say that it all depends on the application. So for specific applications where we need high speed processing at the cloud level, I doubt if organic memories will replace non-organic based technologies, because organic materials are typically slow. Organic materials are also temperature sensitive. So there are several applications where I doubt organic memories can be used, for example, space applications, etc. Other than that, if we talk about flexible applications, wearable applications, where edge computing or storage locally in a wearable device is needed, where high speed is not an issue, is not a requirement. I think in those cases, organic memories can be used if it is cost effective, of course. So
this is a question again from the audience, and this is for Bhashar, right? Or I will ask Bhashar to take it. Reliability is the major issue for our RAMs. How can we overcome reliability issues?
yes, exactly. So that's again that's a good question. Reliability. When we say reliability, mostly what I would say is the drift in resistance from cycle to cycle, the drift in the on-off parameters from cycle to cycle. That is a major issue if we consider this like a filamentary. I would say that there are strategies. Groups are investigating different strategies. One is to be within the filamentary domain and try out ways to confine the filament in a certain region using nano channels or using some other strategies. For example, there was a paper from MIT, correct me if I'm wrong, where they used that if you have a single defect in a silicon germanium material, then only through that region the device switches, and that reduces variability. So there can be different materials engineering strategies within the filamentary RRAM framework, and people are investigating that. Another option is to go from filamentary RRAMs to interfacial RRAMs. So interfacial RRAMs will not have that fluctuation because the filamentary switching is more related to the interface properties between the metal and the dielectric. So mainly Schottky barrier modulation, that kind of thing. But the filamentary switching has the advantage of better on-off ratio. So right now, that remains a challenge, I would say. That is an open question, but I would say that there are strategies that people are working
on. Okay. So I think with this, I believe we are running out of time. Correct me if I'm wrong.
Yes.
Right? What time does this end?
Yes.
It's about now, right? So, this was, thank you for a very engaging discussion. This is great. And I wish your research all the best. Looks like there is a lot going on. And with that, over back to you, professors.
Okay. Thank you, Professor Guha. Actually, certainly we will stay back for some more time to answer these questions, and then I will extend some more time. Probably as an official discussion, maybe we can close at this point in time, owing to the time constraints. And thank you so much for taking time to join with us and throwing some of the interesting aspects, particularly developing hardware accelerators. Certainly, it's one of the major milestones to move forward in terms of high-speed computing devices. And we would look forward to have you on the campus in the future, for future discussions, and we'll look forward to meeting you in person.
I will look forward to visiting as well. Take care.
Thank you so much. So, Bashwar, shall we continue to answer some of the questions, or should we? How do we
answer a few more questions?
Okay. Can you read one by one? Probably you can.
So, yeah, I will read from the beginning. So, racetrack memory using Hall effect, is it possible to produce it commercially?
Okay. Yeah, so certainly yes, there are potential avenues to have this as a product, but in terms of looking at a candidate which can satisfy high density data storage solutions, this may be a little a difficult avenue for a racetrack memory, because we will have to have either on two platforms. One is 3D exponent memory, it should be vertically scalable, or otherwise multi-bit data storage. So in both of these cases, racetrack may not fit into to those types. However, owing to better programming speeds, certainly racetrack memory can be, can find a niche space in the market to provide high-speed computing.
Okay, thank you. So the second question is, which memory is better to use in research activities? That is a tricky question.
A tricky question. So certainly, we would be happy to comment on that as phase change memory, resistive random access memories, and STT-MRAM. So these three candidates would be a possible avenue to move forward, both research aspect as well as commercialization or technology development.
So I will go to another question which sounds interesting. How do memory technologies help in self-repairing space shuttles, unlike software safeguards like artificial neural networks? This may sound like science fiction. Okay. So I am not exactly sure what self-repairing space shuttles mean in this case. If it is a question about this shape memory alloys, that is, I think that is a completely different domain altogether.
Okay, maybe partly I can comment on the use of emerging memory technologies for space applications. Certainly, this is one of the avenues have been looked at very carefully, and it has been successful to see that these candidates have been able to withstand radiation effects and has the potential to be used in the space applications.
Exactly. So it can be definitely used. Okay. What is your view on organic materials? I think we have already answered that.
Yes.
How semiconductor material can be used for memory? Okay. Shall I answer that?
Yeah, please.
So compound semiconductors can be used definitely for memory devices. For RRAMs, I know for sure. For example, aluminum nitride or gallium nitride, they can be used for instead of using oxide-based RRAMs, people can make nitride-based RRAMs also. And the principle is somewhat similar. In oxide-based RRAMs, generally oxygen vacancies lead the switching. In nitride-based devices, it is a similar mechanism, although we do not have access to oxygen vacancies, but it is certainly possible. So, what percentage? Oh, there is one interesting question. So maybe.
So, can you read the question?
Where does the 3D memory
could be used in?
Used in
consumer products where they aim to reduce the overall size of the product. Okay, so essentially, if you look at the conventional 2D memory, you have a selector device along with a memory element. So the selector device is a transistor. Now, the important question is, how do you scale down if your memory is capable to scale down to much smaller dimension? Because the stack of a single transistor along with a memory will have a bottleneck situation. That's where the point of developing 3D point has come into picture by replacing the transistor with a thin chalcogenide material can act as a two-terminal transistor, yet provide a solution of better scaling compatibility. So that's how the 3D point memory can provide high density, high speed, non-volatile memory solutions. When once we have such feature, that is certainly possible to look at an avenue to replace the existing, number one flash memory, as well as in the future, the existing DRAM itself. So because we can envision the speed of 3D point memory in the range of or closer to the DRAM itself. So it's obvious that we can look at 3D point as a potential candidate to replace DRAM in the future.
Thank you. So, there is one question that is also interesting. So what percentage of memory of human memory system we are able to understand? If everything will memorize artificially in gadgets, will it affect our brain memory system? So what percentage of human memory we are able to understand? That is, again, that is a difficult question. I mean, so there are two aspects of this question. One thing is whether, so one thing is that we are trying to build artificial memories, right? That can have several applications, such as in artificial neural networks or in digital storage. Another question is whether we understand ourselves or our memory. These two can be correlated, although they don't have to. So we certainly do not understand human memory completely. There have been a lot of research going on in the last 100 years or so. But at the same time, for artificial neural network applications or for digital storage applications, we probably don't need to. So I will leave it to that.
Okay. Yeah, there was a question on so about the heating in phase change memory. There was a question on PCM devices needs heater on chip. Is it a problem for achieving high density? Okay. So certainly, if you look at the programming strategy, there are different types of cell structures that are available, namely mushroom type or micro trench or core-like structure. In the mushroom type, you do employ a heater. This is essential to heat the material to surpass the crystallization temperature. But there are material combinations that can produce self-heating to surpass the crystallization temperature. For example, the silver indium doped antimony tellurium, the second family of phase change material, provides programming strategy without a heater itself. So there are such literatures available in the to read, and these work were carried out by Philips at Netherlands.
Okay, so there is one question on whether RRAM is cost effective or ineffective in future. So for any technology to be cost effective, you need, first of all, technological maturity, and you also need to replace the old technology. So that's where the price also becomes huge. So right now, flash is the dominating technology in non-volatile market. So, and flash has been there for many years. So if we want to completely replace flash using RRAM or PCM, it will take time. So it is not a one-day process because industry will take it up slowly. It will be a gradual process. And in the meantime, both of these technologies will continue to evolve. Some of the issues that we have mentioned today, strategies will evolve to address these issues. So at some point, there will be a jump from the flash to other emerging technologies such as PCM or RRAM, but it is not an immediate effect.
Okay, so there is a question: which type of memory used by space satellite for storing their instructions? You want me to go for this? Okay, certainly. Any emerging memory technology that has to be immune to the radiation effect. So this is one of the key requisites. And if you look at both the memory technologies, RAM as well as PCM, primarily it is the structural change from amorphous to crystalline or from the disordered to ordered structure, which provides the information storage. And to some extent, when the cell size is significantly optimized, then the radiation effect can be negligibly small as 0. So those kind of emerging memories can be a viable platform to be employed in satellites for computing applications.
So there is another interesting question about quantum error correction. Let me see if I can see that question. Okay, how can we relate quantum error correction in terms of memory technologies? Do you want to?
I'm not able to understand the question actually.
I think the question is, yeah. I think the question, if I'm not mistaken, is asking us whether quantum error correction can be done with these memory technologies. That is the question. See, quantum error correction will happen in quantum domain, and PCM or RAM, mostly we're talking about classical domain as memory technologies. So both PCM and RAM can be used for cryptographic applications, for this physical unclonable functions, this type of applications. But for quantum error correction, I'm not exactly sure how we can relate these two memories, unless we have a quantum resistive memory or quantum PCM that shows quantum effects.
Okay, I think we can probably end at this point in time. So can we call the
Yeah.
Lisa?
Yeah. Shall we close it formally?
Yeah, I think we can close it formally. And if there are any other queries, of course, the participants can write to kamakiitm@gmail.com.
So could you please put it in that, chat?
In the chat, okay.
Yeah.
In the chat or Q&A?
Chat. We can chat.
Okay.
You can put to everyone.
Yes. So I sent email ID. So feel free to write to your email ID for your queries, and we will be happy to get back to you.
Yeah. Thank you, all the attendees. I mean, you have asked very interesting questions today, and if you are interested, please feel free to contact us.
Yeah. Thank you, Dr. Anbarasu, and thank you, Dr. Bashar, for the wonderful session today. And we had really, it was very lively, and we had a lot of questions, and you had answered everything as patiently. Thank you. Thank you, participants. Kindly check in the link tree for further webinars in IRIS series. Once again, thank you, everyone.
Thank you.
Yeah.